All right. Well, welcome back. And Dr. P here, of course. And in this lecture, I want to talk about base strength. Now, just like we did with determining acid strength, we can look at the structure of the conjugate species and see what does a better job of stabilizing. In this case, it's going to be a positive charge. So let's just take a look at this real quick. So let's say we had some sort of base plus H plus, and that's going to give us BH plus. Or we've got something, let's just call it, I don't know, some other base. A plus H plus gives us AH plus. And so the stronger base is going to have, just like we saw with the acids, the stronger base is going to have the more stable conjugate species. Now I should make a note that more stable is the same as saying weaker. So the stronger base comes from the weaker acid. So we can look, and I'm not going to go into too much detail about this, but we can apply REO to look at conjugate acid stability. There are some slight differences here. First of all, for atom identity, since we're going to be stabilizing a positive charge in the conjugate species, a less electronegative atom will better stabilize the conjugate, let's say, better stabilize positive charge. We'll also still have a larger atom will still better stabilize a positive charge. So that's the only difference there. Maybe I'll make a note of that. Larger atom will better stabilize positive charge. So an example of this, let's look at NH3 versus H2O. And if we look at our conjugate acids, we've got NH4 plus versus H3O plus. And so this is more stable due to positive charge on less electronegative nitrogen, which means that NH3 was stronger base, or is stronger base, I should say. Okay? So you can do, similar analysis. Again, the atom size, it's the same trend that we saw for stabilizing a negative charge, because it's all about spreading out the charge. But we have the opposite trend as far as electronegativity is concerned, because, well, electronegativity is the tendency of an atom to pull electron density towards itself, and that's not going to stabilize our positive charge. All right. Let's take a look at the next category, which is, of course, resonance. And in the case of resonance, just like with acid strength, delocalization of the positive charge is going to make something more stable. So I won't go give you an example of this because it's essentially the same idea, except this time we've got a positive charge spread out over more of the molecule. And then we have induction. And this is going to be pretty much the opposite of what we saw with the acid strength. So let's call this, we'll say electron withdrawing atoms / groups will destabilize the positive charge. On the other hand, electron donating groups will stabilize the positive charge. So what would that look like? Well, let's say we had something like let's do it this way. If we had something like trimethylamine, carbon is not very electronegative. So the methyl groups here have electron density from the carbon that actually could be donated to help stabilize the positive charge on the nitrogen. So if we protonate our base and get our conjugate base, now we have a positive charge on our nitrogen. And this should be more stable. So let's say positive charge stabilized by CH3s. And they're stabilized by an inductive effect, namely the electron density from the carbons can move a little bit. Maybe move isn't the right word, but kind of sort of creep over a bit to help stabilize that positive charge. So you would expect trimethylamine to be a stronger base than ammonia. And that's just because the conjugate species, the conjugate acid, should be more stable. All right, lastly, we have orbitals. And let's go back here and let's get rid of that O in REO, okay? Because the positive charge is not in an orbital. An orbital has electrons in it. So there are cases where positive charge could be an empty p orbital. But like in this case, this positive charge it's not in an orbital. We can have a lone pair in an orbital, but orbitals are not going to play a role in looking at the stability of our positive charges. So we'll say here, not important or not relevant. Now, just to sort of summarize, or maybe not summarize, you can apply REO or RE, I guess, and figure out whether or not a given base would be stronger than another base. The other thing that I want to maybe just reiterate is that, let's say here, don't worry about pKb values. Okay, so if you're thinking about acid strength, you may think about pKa values. Okay, the lower the pKa, the stronger the acid. So you'd have the same trend with pKb. The lower the pKb, the stronger the base. Instead, what I do, so I don't have to worry about storing pKb values in my head, instead, think of pKa values of conjugate acids. And remember, the stronger base came from the weaker acid. So, for example, we could compare, let's do this. Let's do CH3, CHH minus versus CH3, CH3N minus. If we look at our conjugate acids, we can see we have CH3, CHH, CH3, NHH. And if we were to look up in a table these pKa values, we would see this is around 50, and this is like around 36. Okay, so lower pKa means it is the stronger acid. So the stronger acid came from the weaker base. Okay, so stronger acid, weaker acid. Weaker acid came from the stronger base. So now we can say that since CH3 is weaker base. CH3 CH2 minus was, no, it's not base, that should be acid, I'm sorry. So we can say since CH3 is the weaker acid, CH3 CH2 minus was the stronger base. So you can use pKa tables to figure out relative base strengths for the conjugate species. So the pKa tables are for acids, but if you look at, whatever is a weaker acid in the pKa table came from a stronger base. So if you drew this, the conjugate bases, you'd see that, again, the weaker acid came from the stronger base. And the stronger acid came from the weaker base. Anyway, practice, because, it does take a little while to keep things straight in your head. And yeah, so I think, we spent a lot more time looking at acid strength and not so much base strength. But this is a pretty good way if you want, something sort of quantitative. So you're not just thinking about the qualitative structural effects. All right. Well, I will talk more about Lewis acids and bases in the next lecture video. Until then, stay safe. Bye now.